So good morning, everyone. Today is a special day in many different reasons. First, it's the last Friday, or the Friday of the third week. But it's also the first day we have two experimentalists talking. So, and we're starting with Karen Daniels, Professor Karen Daniels. Professor Karen Daniels is faculty at NC State, down the road from.
Yeah, we're neighbors.
Right, we're neighbors. She's been doing some. She's been doing mostly granular experiments, but with other purposes as well. In her 2 years as senior faculty, and she's a very dynamic, as you will see, and a very politically involved within the organization of science as well, at APS. So she roped me into running stuff. So if you hang out too much with her, you'll end up with responsibilities. So
yeah.
Just to measure how much you want to spend time. We're good friends also, so it's a pleasure to have her here. So, Karen.
Yeah. And it's a really pleasure to be here, too. So I have to say that it's a little daunting. And when I put together this talk, I was like, well, OK, so I know 2/3 of you guys are theorists. And I'm going to say the word friction like every other word. So a lot of today is going to be learning to deal with the fact that the world has friction. Sorry for those of you who are quantum mechanical, it doesn't. OK. And interrupt me. I've got stuff planned. We don't have to go through all of it. I'll change what's on Monday depending on what we get through today, or if I see you guys asking about stuff. So this can go with the flow as far as I'm concerned. All right. So the first thing so let me write an outline up on the board. All right. So this is what we're going to hopefully get through. So 1, grains have friction, period. Okay, so this is different than colloids and foams and emulsions and glasses. Okay, and I think it has real implications. Okay, and I would love to hear more theoretical involvement in dealing with the implications. So some of this is going to be a call to those of you who are theorists to embrace friction. So the second thing is, not only is there friction, but friction matters. Okay, it does some things that are different. It changes the allowed configurations. Okay. And we should be thinking about that. Okay. So 3, message is we can measure things. We can measure forces and positions and some other stuff. Okay, but I'll primarily talk about forces and positions. Okay, and this is important for those of you who want to be making comparisons to understand what some of the caveats are in that. Okay, and sort of some advice for working with experimentalists. A fourth message is going to be that forces matter. Okay, and then we'll get to some frameworks for understanding the implications. Okay, and so these will hopefully be some tools from network science, some stuff about Edwards-like ensembles, and I'll try to maybe, this is less my work at the moment, but I'd like to talk a bit about Gardner stuff, because it's grabbing my attention these days. All right, so that's what we'll hopefully get through. And my notes aren't up online. At the end, we'll see how far I get today, and I'll put these up at the end of the day, and then I'll put the rest up on Monday. OK, so we're going to start with some inspirational demos. All right, so these are all caveats about real granular materials. All right, so this is a demo that I borrowed, well, not literally, I bought my own 3 balls from Matthias Schroeter And you can tell right now that friction matters because otherwise that center ball would be falling, right? So it only takes 3 particles to see that, okay? You also can do it the other way around. Here the rolly bits start to matter. This is harder to do. There we go. Okay, so friction matters. Okay, it stabilizes configurations that would otherwise be unstable. Okay, so there's a need to understand what the frictional forces are there. If I look at the position of any particle, okay, you can know from the history that friction must be pointing that way if you saw it coming in, right? But if you just see a static configuration of particles, you actually don't know which direction the force is, frictional force is pointing. So understanding the tangential forces will become very important. All right. So how can we measure? Oops, I just dropped a piece. How can I measure frictional forces? So I'll come more to this later on, but I want to give you guys a sense of it right away. So I'm going to pass around this demo. Okay. So this is how you use the demo. You find a light source. You look at it through the light source. You push down on it. I promise you'll see a picture like this. Okay. It's very easy to use. Since you guys are advanced and are thinking about configurations, I'd like you to try the following experiment. You have 2 fingers. You can change the loading on the top plate, right? So I'd like you, once you push down, to wiggle back and forth left to right, just a little bit. And what you'll see is that the forces switch around without switching the configurations of the particles. Okay? Okay? And then you can shake it up and try again, and so forth. Okay? So let's make this go all the way around. And what you'll be looking at is lots and lots of particles. And we'll do the quick version of why this works. It's got circular polarizers on the front and back that are opposite in chirality. Therefore, light can't get through. Okay? Left circularly polarized, right circularly polarized. The grains are birefringent. Under stress, they rotate the polarization of light. So this grain, because he's bright, means that he must have stress on him because he rotated the polarization of the light and was able to get through. So brighter means more force. We'll come to that in more detail as time goes on. Of course, I'll hand it to someone who knows, from Val Behringer's labs, knows this demo well and need not play with it. But he can't resist. OK, so I'm an experimentalist. And so I am willing, but I'm pretty much as bad as the next theorist, because you'll notice that I have chosen to use circles. Okay, and when I'm feeling very adventurous, I minorly break a symmetry, and I'm willing to use ellipses. Right? Okay, I'm not that much more daring. Okay, I don't go that far. Okay, okay, so this is too real. Right? Okay, so we're not going to, don't worry, I'm not bringing you there today. Okay, actually, I think this problem is fascinating. I do experiments on stars like these too. Okay, but we're not going there today. Don't worry. Okay. All right. So, all right. So let's have a mute here for a second. All right. So a couple more demos to get us thinking about. Oh yeah. There's also, for those of you that don't like statistical mechanics, I also have the single particle version of the experiment, which is easier to see how it works because you can push one of them at a time. All right. I know all of you like statistical mechanics, so I don't. All right. So some other ways to see that history matters. Okay. All right. So I just told you we were going to do spheres. We're not. This is sand. Okay. So what we have here is nice flowing sand, right? And since it's obviously a liquid, I'm going to pour it into this nice glass. We're going to stay nice and hydrated here in Boulder, right? Okay. And right, so if this were a straw, and I were to pull it out of my glass of milk, we all know what would happen, right? So what do you guys think? I poured it in. Do you think this is stuck or not stuck? What's going to happen when I lift up on the straw? Vote. How many think this is going to pull out, and how many think it's going to stay in? So how many think it's going to slide right out? How many think it's going to stay in? The sand's nice and solid. How many of you don't want to vote? Okay. All right. So that's a terrible solid. Okay, so all of the stuff we've been talking about, rigidity and so forth. Okay, so only about a third of you were right. Would the rest of you like to be right? Yes, you would. All right. So we'll do the experiment again. Okay, and last time I did it, you guys were wrong. But now we're going to make you happy. And this is how I'm going to make you happy. Okay, so tapping it turned it into a solid. Okay, now unfortunately I can make you wrong again. I can tap it some more, and you're back to being wrong. Okay, so this is just play sand. That's actually ashtray sand. Anything like rice, sugar, whatever you have around will work to do this. It's pretty insensitive to the details. Okay, so the history of how you've prepared the granular material has a big influence on its mechanical properties. All right, I will leave these demos will all be hanging. I'll leave them in a box in the back, and then so you guys can play with them during breaks and so forth. All right, so make sure I check off my list of points I wanted to make about. Okay, so we're seeing that friction matters, history matters, right? Probably, okay, the mobilization of frictional contacts and which direction they point play a role in some of that history. We'll get to that probably on Monday. Okay, and the last thing I want to bring up is whether or not this is disorder is in the title of this workshop. So I showed this with some pause after talking to Jorgos last night about on his poster. So he would not agree that these are crystals, but they were what I would call a crystal, as in Eli Owens, the grad student who took the data, put 300 of these photoelastic disks into a box, into a nice hexagonal array, and then loaded it from the top. Just put a heavier weight on this one, and I think a very light weight on that one. Okay. And what you can see is, even though the particles are ordered, is the transmission of forces ordered? Well, there's places that it is, right? Okay, but there's also places where it's not. Okay, and so any place that you have small amounts of disorder, okay, in any real material are never perfect circles, right? You're going to generate disorder in the force change that is far more apparent than the disorder in the crystal itself. Okay, so that's a caveat. All right, so let's talk about. So now we're going to switch to a bit of board work and talk about how to model these contact forces. All right, so this is news, not news to many of you, but let's see. How many? Okay. How many boards are there? 2? 3. There's 3. So how do you rate on the third one? Oh, I see. This one is listable as well. Okay, good. All right. You can tell I do not work at a university that has rolling boards. All right. There's a light switch. I should also use that. Cool. All right. So, granular contact forces. Right, so start with normal. Okay, many of you, so these are Hertzian contacts. Have you guys done this already? This is known? Not, okay. Right. So if you want more, good sources are Landau and Lifshitz, or Johnson. There's a book called Contact Mechanics. So if you want to go into the nitty-gritty details of this. Okay, so basically the idea is if you have 2 grains not in contact, okay, and they're of radius r, if you put them into contact, okay, there's an overlap of size, what's often called the overlap, which of course is a lie. particles don't overlap, right? Particles, in fact, deform. So the real thing is that there's deformation, but people call this overlap. Okay, so that amount of overlap delta. Okay, so for linearly elastic spheres, okay, if we're pushing with a force F diametrically, okay, this is the modulus, this is the Poisson ratio. Okay. So this is why you've been seeing in the jamming talks this exponent coming up. Okay, it comes from that normal context force that is the solution for linear elastic spheres. Okay, if we want to do disks, F is proportional to delta. Okay, the same solution. Okay, and the homework that I'm not going to assign is actually in Lendo and Lipschitz. You can actually go and show that. So if people want that, I'm happy to give that. All right, so let's look at what experiments say. All right, so here's a couple different people's measurements of it, not just mine. So here's a measure of force versus displacement. The red points are the real data. This is from Bob Behringer's group. And I don't know. So the question is, do you want to call it something that is fit by a nice power law? 1.54 is very close to 1.5, right? Unfortunately, these are not spheres. These are disks. So the good news is 1.54 works well. The bad news is it wasn't supposed to work. Okay? So what they prefer to say is that actually what you're seeing is a bunch of closing off of asperities, right? And then eventually the linear part kicks in. Okay? So that's one way to interpret the data.
Their disk is really that rough?
Well, that's the question. Like this, I mean, that's a tenth of a millimeter, right? So it's not rough at the scale of tenth of a millimeter. So something's going on here, right? So these things aren't perfectly Hertzian. All right, so this is data that we took, and we stuck it on a log-log scale so you could better judge the slope. And we were like, well, 1's okay, but 5/4 is probably better. Okay, so why this map? So if you imagine now you're squishing two disks together, what are the chances that you have them exactly on a flat plane? Not very good, right? So if you had them perfectly 90 degrees, cylinder against cylinder, you'd actually expect a larger exponent. So these larger exponents are largely coming about due to slight misalignments. Out of 2D motions means that you're doing cross cylinders, not cylinder on same parallel axis to the other cylinder. Okay. So in general, while these are the exponents people use, okay, the data for that being literally true is not fantastic. Okay. And so so that's a caveat. And so I would say, so that you could think of something as generalized, which is what, in fact, the jamming framework as well. You could pick your power up there, as you will. Okay. All right, so that's the normal forces. Look at the tangential forces, okay, which is also just completely classical, right? This is just Coulomb friction, right? And that the tangential force has to be less than or equal to the friction coefficient times the normal force. This is nothing different than you learned your first year of physics, okay? This is annoying, right? And most contacts aren't at the point of failure. You can't just replace that with an equal sign or something and be done with it. So I, in preparation for this talk, asked my postdoc, Jonathan Colmer, to just make me a plot of some of his data so that we could take a look at it. Okay, so this is for one of these photoelastic systems for which he knows all of the contact forces. I asked him to make a 2D histogram of what values were measured for the normal force and the tangential force. Okay, so yellow means lots of that, blue means none of that. And so from this we can see that they rarely, this line here, there are some probably experimental error dots up there, but this line here, where this intensity falls off, corresponds to a mu of about 2. Yeah.
So this is taken from experiments with the
It is, yeah.
So how do you get which part?
I will cover that down the road, yeah. Okay. So suffice it to say, we can measure that, as can the Behringer group. There's a number of groups that can do this. Yeah. And so, but be aware that there's basically everything in here is populated. Okay. And if you look at systems that are prepared under different preparation protocols, how this is populated will change. Okay. All right. So what do simulations do? Okay. So just like over there, actually the simulations do something that makes a lot of sense. So we want to put this all together. So simulations, you know, what people in the engineering community usually call DEM, but are just a generalization of molecular dynamics methods. Okay. They use what are called Hertz-Mindlin contacts. All right. So here's a schematic of what gets coded in. Okay, here's particle 1. Here's particle 2. And this is 2 particles in contact. I know they don't look like they're in contact. That's because I have to have some room to draw them a bunch of stuff in the middle. So these are 2 particles in contact. Okay. And you want to have some sort of friction mu between them. Okay. You want to have some elasticity, and you need to have some damping. Okay. So this is what's called. So this is the normal stiffness, and let's call this eta normal. So this is, so for all of these, K is the stiffness of particles. The etas are the damping. Mu is the friction coefficient, and T and N refer to tangential and normal. Okay, so the normal force is taken care of both by an elasticity and some viscoelastic damping. Okay, for these photoelastic particles, this is actually fairly significant. And this is the one I have harder time drawing. I practiced. Okay, those dots are at the centers of the particles. I promise. Okay, so this is what gets modeled. You have a tangential spring and dash pot, and you have a normal spring and dash pot, and you have sliding friction. Okay, so is that friction? No, it's a model of it. Okay, and in fact, it's not the only model. Corey O'Hearn and his group have, let me go a little aside here, right, have done some simulations where they model friction geometrically, like it's actually frictionless, but they decorate a particle with lots of little spheres, okay, and make, so this has mu equals 0, but geometric friction. Okay. Neither of these is correct, strictly speaking, but they are able to capture a large number of phenomena. Yeah.
Why would you have a tangential list going forward?
So if you take a particle, actually I can show you with this. Let's see. So if I shear this, what happens to the shape of the sphere? it slightly deforms, right? Actually, let's make my particle square for a second. It's easier to see, right? Right. So if I had a square particle and I applied a tangential force, right? What happens to it? It deforms. The same thing happens to a circle. It's just not as obvious. I guess it goes from circle to, I guess it does that. Right. Okay, so there's a deformation inside the material that acts as restoring. So so what is your guess as to the relative sizes of KT versus KN? Who's bigger? KN is bigger, right? Because exactly your intuition that you weren't even sure that this existed, right? It's much smaller than that. So people use values of like 5, a ratio of like 5 for that. Get that a factor of 5 times is often what people put in. So in spite of these being artificial forms of friction, actually they're quite successful at modeling stuff. All right. Other problems. So those of us who do photoelastic experiments, the whole reason that the photoelasticity works, okay, you need to generate a stress field inside the material that's large enough to rotate the polarization of light. That means your particles are going to likely be soft. So here's an example. So you can actually see on this picture the development of a larger contact area, right, as you go from left to right. Okay, and you can actually see that it's not really an overlap, it's actually deformation. Not that you doubted that. Okay, so the particles, in fact, do get deformed. They're no longer circles once you start doing experiments on them. The particles I've been passing out are treated. The single particle one is quite soft. It's about like these. Okay, the ones that are inside the square demo are much stiffer. Okay, and so they don't have as much deformation. They also have less of a photoelastic response, right? So there's often a trade-off doing experiments taking that. Okay, another caveat related to this geometrical friction thing is that, all right, what sets the friction of two particles in contact? I give you two glass spheres. What's the friction? How would you find out what the friction coefficient is? You do an experiment, you'd push them against each other. You do the freshman physics experiments, right? Okay. You might even just look it up on a table. What's the friction of glass, right? Okay. You might do an angle of repose experiment, right? Okay. What's the angle of repose? Okay. But you would think that if I buy glass, and I keep buying that same glass, I can label it with a coefficient of friction. Do you agree? You hope, right? Okay, which is why when you etch that glass, the coefficient of friction definitely doesn't change. Wrong. Okay, yeah. Etch means you dunk your glass spheres in a highly chemically active fluid, like in this case hydrofluoric acid or sodium hydroxide, okay, which starts to dissolve part of the surface. So it doesn't really chemically change the surface, but it eats away part of it. So these are experiments Matthias Schroeter did, where he started with an untreated, just glass beads that he'd bought, and he bought super perfect glass beads, like the best super perfect glass beads you can buy. Okay, some of them he smoothed using sodium hydroxide. Some of them he etched to be rough using hydrofluoric acid. Okay, so this is smooth, medium, and rough. All the same material from a chemical perspective, just changing the roughness. And depending on how long you etch something, right, you can change the coefficient of friction, okay, by 10%, right? Okay, so coefficient of friction itself is possibly not the most well-defined quantity anyway, okay, and in any real experiment has a lot to do with the history of how that surface of the material has even been treated. Okay. So that's really depressing. Sorry. Okay, so we're not going to. This is the end of the depressing parts. Okay. The fact is that it's good to keep in mind that all of these are going on, okay, so that when you're looking at phenomena, right, and if the errors in what you're seeing depend on a 10% change in coefficient of friction, should you be concerned? Not at all, right? So this gives you some sense of where things are reliable, where things aren't reliable. Yeah?
Maybe clarify, in like first lecture of classical mechanics, we learned that we have have static friction coefficient area.
Yes.
Like, the more kinetic one.
Yeah.
So, like in the experiment, which one we are measuring?
So that depends on the experiment, right? And so you can people can measure both, right? And they are actually different. And so in fact, I haven't told you the whole story here, right? So people who are doing discrete element simulations have the option, of course, to decide whether they use a kinetic. If they're doing a dynamic process, right, you're going to want to use a kinetic coefficient of friction. But they have the choice to use those, yeah.
But like their response to the roughness.
This was a static coefficient of friction. This was static, yeah. So I've glossed over that detail. So that's yet another difference where one must pay attention to what you're doing. Yeah. There's also velocity-dependent coefficients of restitution. So this damping here depends on the velocity of collisions. Right? There's a whole host of problems. Yeah. I just don't want to get you too depressed. All right. So the experiment I've been passing around, I asked you guys to do an experiment where you squish down slightly differently without changing the packing inside, right? And so what did you guys see happen? Yeah, so you could switch where the first chains were, right? So we're actually doing a formal version of that experiment right now, okay? So we have a bunch of these disks floating on a very gentle layer of air, okay? And they're in a little box, and we move a wall out, and then we move the wall back. And then we move the wall out, and we move the wall back. And we do this 1,000 times, okay? So we did this experiment you just did 1,000 times. And here's a movie of that. Okay, so this is now just a movie of each of the 1,000 final states. Okay, so this is what you guys were seeing, is that the force chains, go slightly different places, different times. So this is an athermal system. There aren't temperature fluctuations driving this. The fluctuations you're seeing are just from small sensitivity to initial conditions type things. Just how tilted was one disk on its way in, right? Did some small air current push it to the left, push it to the right? Okay.
These are all spherical.
These are all disks. And of course, we've just discovered they're rough. They're not perfectly circular and all that, okay? And in fact, if you watch really carefully this guy, can you see some little black dots orbiting? Okay. So the reflective coating on the bottom of these is not perfect, okay? And so they have imperfections. So visually, you can actually see that these particles are not staying in the same orientation. Okay, they're rotating around. So that they're clicking in on different disparities even each time. Okay. So we'll come back to this later. Yeah. Yeah, so if I use monodispersed particles here, what do you guys think would happen? 2D. 2D. I'd get a beautiful crystal, right? And I would also not get the same force chains each time. Because again, there's small disparities. And so whether or not the left guy or the right guy gets the force, will change from time to time. Yeah.
One question about, so in the right side of the sample, there's this like force chain that remains pretty consistent?
Yes. Yes. So why? So do you guys agree this guy is super popular?
Yeah.
But either by the end of today or on Monday morning, I'll tell you why he's popular. Okay. And it's not because he's a good football player. All right. Okay. So yes, you're right. You're exactly right. So we've been after explaining that exact thing, and we think we know how to do it. All right. Yeah.
How large is the particle?
These are basically a centimeter. Yeah. So they're 11 and 15, I think, millimeters.
How large is the change that you're making?
Very small, actually. So if we open the box too much, guess what happens? It changes. So we've tuned this carefully, right, so that we open the box and they can rearrange force chains, but they can't rearrange their neighbors. But this is related to what question that's been going on a lot. Here, it's like how far I open that box, right, should tell me something about the basins. And we are actually starting to investigate that with Patrick and his postdoc show. Yeah. So you guys are all on to the same questions we think are interesting. This is awesome. All right. So you guys now have 3 minutes, and I want you to do the following. With your neighbors, okay, brainstorm what properties of a packing, okay, are either easy or hard or unknown or known or the same or different if you're doing experiments, for instance, like I just showed you, okay, versus doing simulations. So brainstorm a few things. Go.
Very slightly equally dispersed around the two main values. They're also on here.
Well, yeah.
All right. So let's write a list. So who's got one they want to put up here? Patrick does, of course.
So experiment scale like the size of the system to the 0 power and simulation by linear power.
Okay, so this is so we'll call it computational difficulty, computational complexity, computational complexity. So for n particles, right? So this is, and I would n to the 0. Now, I think my department head would have some beef with that. I don't think he's going to give me space to build an experiment to model Saturn's rings. Okay, so caveat there. All right, simulations, we have order, and you want to write n to the d here? Or
No, n or worse.
N or worse. Right. Yeah.
Actually, to do an experiment, it takes a lot of time to rearrange this
and the data processing time, right? Okay. The data analysis isn't any better. Okay, taking the pictures is super simple, right? Super simple. We had that picture I showed you 9 months ago, right? But before we got around to understanding it was this summer. Okay? So just to give a sense, and that's in human time, not okay. All right, other things. You guys, packing fraction. Okay. Well, let's think about that. So how would you measure it in experiments? You count the number of particles. Presumably you weighed them before you put them in, right? You know how big they are. You know how big your box is. So the global packing fraction, super easy, right? So global is easy. You're talking about the local one being hard, right? The local packing fraction, you have to be able to see inside it, right? Okay. And for simulations, easy, right? All right, other things. Positions, yeah, and I think so. This comes about because finding the positions of particles. So this is actually what leads to that being hard. Is that this is hard, and this is easy. Yeah. Vibrational modes. Yeah. So this is even worse than positions. So hard. Okay, easy is a bit of an exaggeration. I'm saying relative hard and easy here. None of these are actually easy. Yeah.
Determining the contact.
Contacts, yeah. So just yes, no contact. I'm actually going to write here something even worse. This is, and I'll get to why this is so hard. Don't ask experimentalists to tell you whether or not there's a contact. Is actually probably a better description there. And I'll tell you how you can do something about it. Okay, but it's not a good situation actually. So we hate Z. It is actually hard? Okay, hard to do well. Okay. So great. Everything all this information depends on Z, and we suck at measuring it. Yeah. 3 dimensions, yeah. Okay, so how am I going to do this now? I guess I start erasing. All right, so 3D is hard, and I would say this is it's still harder than 2D, okay, because of the computational complexity problem. So we won't want to make that nothing, but it's very hard. I'll tell you guys some techniques for doing this. As you know, there are techniques in 3D, but they're tough. And higher dimensions, of course, become possible. Sorry, Eric. All right. Other ones. Back of the room. What? Forces. Right? This is just not like, God, no one should do experiments. Next one, someone has to point out something the other way around. Is it the other way around?
Yeah.
Yeah, good.
Serendipity.
Serendipity. Which one do you think is better for that?
Experiments.
Yeah. Anyone who's done experiments has done an experiment where you're like, well, that wasn't supposed to happen. I'm going to go study that. So the reason I started studying granular segregation was because I was trying to put polydispersity into a granular experiment, and it refused to stay where I put it. So I just turned it into a segregation experiment. Okay? Okay. There is serendipity in simulations too, right? You guys can probably think of times when something happened you didn't expect it, right? So, right? You don't think that happens in experiments too? Yeah. Okay. So it's less common, right? Yeah. So in some sense, an experiment can't be wrong. Right? It might not. I mean, it's really what happened, right? It might not be that it was a good model for the thing you were trying to test, right? It might be that the fact that it's 90% humidity in North Carolina in the summer, and the humidity caused my particles to have adhesion, and therefore the experiment didn't do what I wanted it to do. But it doesn't make the experiment wrong. It just makes it a different. You can measure things wrong, right? Yeah. Okay. But you're not going to have a indexing error. Right? Where you just saved the stuff into the wrong array. Right? So in the analysis, it's certainly true that you can have that go wrong too. All right. Other things.
Realistic stiffness dynamics.
Yeah. So I would just let's say things like, let's say friction and stiffness and dynamics. And I don't think I want to say these are easy or hard, but they're sort of unknown here. And they're known and they're controllable. But they're not accurate, not actual. So this is an interesting pros-cons pair, right? It's real, but you have no idea what they are. Right? They're not real, but at least you know what they are. Right? How about, God, I love that experiment. I want to try it again with just slightly different conditions. So do-overs. Do-overs, or even ensembles. Right? And so I've showed you a way that we are starting to generate ensembles. Okay? But that's tricky. Right? You can just rerun the code a second time with slightly different initial conditions, right? And I saw several posters on this, right? Tricky, doable. It's time-consuming, but it's doable. Right. Anything else? So let me see if I've got things on here. Together with forces, I would also say and what the associated potentials are, right? Yeah, Sid.
Just seeing anything inside a 3D.
Yeah, so this is card you can't see. You just plain can't see. Okay. There's another problem here that even if you can see, and I'll talk about X-ray tomography a little bit, if you can see, the same problem for those of you who do simulations, if you go up from an n by n system to an n by n by n system, it gets computationally more challenging. Well, guess what happens to the data analysis? Same problem. You need more storage, you need more processing time, right? So those same computational complexities that arise in simulations, experimentalists suffer from as well, even if they can get the 3D data. Right? It's just as annoying. And I learned this hard. I've started working with some 3D data. I've been 2D person for most of my career. And I have to say I hate 3D data. Right? I get lost. I can't see where I am. Right? It's just, and those of you who work in 3D simulations are familiar with this. And I don't know what Eric does. Right? Just plain get lost. All right. So excellent. I love this list. Somebody should save this. Oh, actually, I have one more I had thought of. Boundary conditions. This came up last night in some conversations. You have some nice periodic ones here, and we're pretty much confined to finite. Yeah. Sid?
Well, one of the things you say like 2D, but in 2D you always have the front and back wall, basically.
Yeah, so that's actually, so that's a bad, so this means that, and so in 2D has a wall and it's only quasi 2D, right? And this isolated of the contacts being slightly out of alignment, giving you weird force laws, right? Okay, so so it's hard, easy. I'd like you guys to think about it as something as a challenge, right? So can you, in spite of the fact that one of these says hard on either column, you want to be smart when designing some sort of study to pick the right tools for the right job, right? Okay, and there are things that are great experiments and terrible things to do in a computer, and there are things that are the other way around, right? So going and tracking down vibrational modes in an experiment is not a recommended activity, right? And it does blind us then to what kinds of things we study and what sort of comparisons we make. All right. Cool. I'm glad this is getting recorded, because it's a nice list. All right. All right. So how particle position data actually gets collected. So here's just some things to flesh these out a little bit, some quick pictures. So here's a picture, actually from that same, still, I think from that same movie I just showed you. That movie is taken in red and green channels. The red shows the particles, the green shows the force chain, so I just took the red channel here so you could see it by itself. So, are these two particles in contact? So what sets your ability to do that? The resolution at the pixel scale. So like the size of your pixel, right, relative to your particle, which is an experimental decision, right, will control this. Okay? How people get 3D data. So there are lots of groups now taking 3D data in tomographs. The way it works is you stick your sample on a turntable. Okay? You fire an X-ray beam at it. Your sample turns around. Okay? The camera takes a picture each time it goes around. It takes those images, does a radon transform, and turns them into cool things like this. It should work if I click on it, and of course does not. Doesn't like to do that in video mode. Oh, I see. I'm not connected to the internet for some reason. All right. Okay, we'll skip that in the interest of time. The link will be there in the talk for you guys to click on. All right. So a lot of people use what are called microtons, which are basically this big. They have a little place you stick your sample in, you close the door, it spins around, you get your data. Okay, those are limited. You can't have a very strong X-ray sitting in your tabletop in a building. There's federal regulations on that, and also limits on how much power your building has. So if you want to take really high resolution data, and if you want to take data that has dynamics, the best thing to do is to head to some sort of synchrotron facility. Okay, so difference in size is considerable. And if you go to, for instance, Grenoble at ESRF, there's a spot there, or if you go to Argonne, lots of places have these. You can actually sign up for time. Okay, you apply for time. It comes with the scientists who know how to run the beamline and know how to do it, so you're not expected to be the expert in that. Okay, it comes with expertise, and you can conduct your experiments there. So those of you who want 3D data, it's a thing you can do. It involves staying up all day and night for 3 days in a row, unless you recruit some buddies. And so you can go to Grenoble and never see the mountains. Okay, so that's one way to get 3D data. Another way is to submerge the whole thing in an indexed match fluid, shine a laser sheet through it, and scan the laser sheet through the sample. Okay, and then you'll collect pictures that look like B. That's just one slice. Then you assemble those, okay, into a 3D packing. Okay. This also requires scanning, so it's fairly slow. It's not good for dynamics. Okay. So this issue of 3D stuff being hard, dynamics are particularly hard, because all of the techniques we have for seeing inside them are very slow. All right. Why is this slide's a little bit out of order, actually. Okay, so this is supposed to be next to the contact picture. So let's say you've taken some data, and you've found the centers of your particles using, say, correlation techniques or Huff transforms or some such thing, and you have a list of x coordinates. Right? These are the x coordinates of all of my particles. So how can you check how good your resolution is? Okay, and this is something that people who are doing simulations, if they're working with someone who's doing experiments and they give you data, you can check for yourself. Okay, it's a nice little trick. Just take the remainder of all those coordinates and plot a histogram of them. Okay, and if you see something like this, that from 0 to 1 pixels, you're most likely at 0 and at 1, and you're much less likely to have gotten 0.5. This tells you have 1 pixel resolution. Okay, if the histogram is pretty flat, okay, you might decide you have 1/10 of a pixel resolution. Really good particle trackers like Mark Shattuck can get better than that, better than 1/10 of a pixel. Okay, 1/10 of a pixel is doable. Better than that gets super hard. Okay. If you're talking about contacts and you want to know that there's a contact, you have to know whether or not it's 0. You're only ever going to know 0 plus or minus the resolution, right? So this is why the contact problem is so hard.
Does this also kind of depends on the size of the particle is? If your particle is like 2 pixels wide,
yeah, so it's the size of your particle in pixels. Right, so that's what I'm talking about. So it doesn't matter if your particle is a centimeter or a micron. What you care is how many pixels across it is, right? And so that's a matter of choosing your camera lens. So for the experimentalists in the audience, your choice of camera lens and sensor size on the camera and all sorts of stuff play into this. But I'm sort of talking about from a perspective, if someone gives you data and you want to know how to trust it, to how many digits of precision, this is a really neat little trick. Okay, yeah. And it can be improved by getting more pixels per particle, which then might mean you need to buy a better camera, right? It can, there are ways to do this. So if it's something you care about, if you really care about getting a shot at contact information, right? The more pixels per particle you get, the better off you are. All right. All right. So all right. So actually, let me make that a little more formal. I think this might be helpful. This is. So let's draw a picture over here. Right, so if I have 2 particles, and here's the vector to one of them, here's the vector to the other, right? And these are particles of radius r, right? Then there's a contact when RA minus RB is less than 2R, right? So if you have errors here, right, this makes it a problem in the, so errors in these give you errors in contact. Does that make sense? Okay. the other nice thing, so if you collected the positions, you might think, in fact, this is just what I was calling delta on the board I just raised, right? So this should tell you the force, right? Okay, so if you have good enough contact information, that may in fact be possible. Okay, so let's talk a little bit about how you actually measure interparticle forces. So the first one is exactly as easy as that. Okay, if you've got good particle position data, okay, and these are examples from 3D X-ray tomography, right? And you're measuring the deformations of rubber balls or of emulsions, right? Either that contact area, okay, or that deformation can tell you what the force is, okay? And you have to do a calibration, okay? So you need to take one of them and squish it and find its force law, and then force versus displacement, and then calculate your contacts and how far displaced they are. And this is totally doable. Okay, it's tedious, but totally doable. Okay, so in 3D, that's actually the best method. Okay, you fit shapes, you find centers, and you go ahead and do that. Okay. And now I'm going to explain to you guys how the demo is working, because I think it's made it all the way around. Okay, and in 2D, we have this neat trick of photoelasticity. Okay, so this is how it works. What you guys were looking at was a birefringent disk between a left and right circular polarizer. Okay, so if you shine light through it, and you used an eyeball instead of a digital camera, the more you push on one of those particles, and the single particle, you can actually do this experiment. So keep passing it around if people want to try it again. And the more you push, you should have seen the more fringes you get, right? And so at a simple level, so here's data from single particle experiments, and this is pseudo data, which was reconstructed. And so we know that if this was the picture we got here, then this must have been the force. And in fact, we knew the force was here because we did it between a little force tester. Okay. So we can actually calibrate this. And in practice, when you do this, you need to know a bunch of numbers. Okay. So let's talk about why this works. All right, we actually can vote. Do you guys want to go into the optics of why this works, or is the hand-waving explanation enough? What?
What are we voting?
Do you want? Oh, I see. So yes, a little bit of optics segue, or no? Yes, optics. Okay. Short little optics segue. All right. So this turns out that this is state-of-the-art 1941. So the great block Frocht 1941. Okay, this relies completely on classical elasticity. James Clerk Maxwell was actually the first person to write about photoelasticity. He talked about it in fish bladders, having this nice birefringent property. Okay, so this is turn of the 1900s. It's awesome stuff. Okay, so imagine the following. You've got light coming through, right, and it's got left circular polarized, right? So if it continues straight through and hits right circular polarized, you get 0. So it needs to rotate by 90 degrees to get through, right? So every 90 degrees of rotation, you get a maxima, a minima, a maxima, a minima, right? So that's why you're seeing the banding. And so if you do the math on that with your proper stuff, you get that every spot in one of those pictures, okay, so this is I of x comma y is equal to some intensity set by the camera. Sine squared, this comes from the fact that you don't care if it's up or down. Okay. Pi sigma 1 minus sigma 2, I'll define these in a second, hc over lambda. Okay, so sigma 1 minus sigma 2 is the local principal stress. Okay, so this is where the classical elasticity solutions comes in. We know, and Frocht has tabulated for just about every situation you can imagine, okay, what the stress field is for a disk with point contact forces. Okay, so those are known solutions. You can look these up. Okay, so these are known for many geometries of contact forces. Okay, H is the thickness of the disk. The thicker it is, the more time the light has to rotate. Okay, C is something called the stress optic coefficient. So high is good, right? You want something that actually has a nice photoelastic response. You don't want to pick a material that doesn't. Okay, so these materials that I'm passing around are basically polyurethane. It turns out to have a very good one. Okay, and actually, C is a function of the wavelength of light, unfortunately. So lambda is the wavelength of light that you picked. Okay, because this says how many times it has to come back around. Okay, now, the images I'm showing you, when we look at this, even though they look black and white, that's often because we have just using a black and white camera or one channel of a camera. They're all taken with filters on them so that we only pick up one color at a time. Yeah? Yeah, so that's actually encoded. Oh, yeah, so it's assuming a linearly elastic disk, too. Yes. So this assumes linear. So for linearly elastic disk, someone could probably do the work to do it for something that wasn't. Okay. So this, but the stiffness of the material itself is coded into there. Okay. So the problem that you have, okay, is that what you want to be able to do is the inverse, right? So if I give you the contact forces, right, you can write down the stress field inside the disk, right? You can plug it into this. You've calibrated this in a separate experiment. That's actually what these pictures are from one of these calibration experiments, okay? And then you can say, if these are the forces, that's the pattern of fringes I see. Unfortunately, which direction does the data go? I've got the fringes, I need to get the forces. Okay, so this is what's known as an inverse problem. Okay, and so this is how we go about solving that problem. Okay. Right. So we've taken a picture. Okay, so the bottom one is our picture. We've separated the pictures, like I showed you. We take a color image where the red light is unpolarized and the green light is polarized, so that once we load up our data, the red channel has pictures of the particles, and the green channel has pictures of the force chains. It happens quasi-automatically. Okay, so using the red images, we actually find all of the circles. Okay, we then take each of those pictures out and just look at one disk at a time. Okay, and each disk we know has to satisfy torque and force balance. We make some guesses for the forces, and then we use a Levenberg-Marquardt optimizer to change those forces until we get the best possible image, okay, by least squares difference between the two, right? And then we give it the next disk, and so on and so forth. Yeah? You're optimizing the difference between these two pictures. And we actually cut out the part right near the contact, because you can see there's a divergence there, right? So we actually put little masks over the edge of the disk and don't include them in the quality control. But that's the optimization algorithm.
What's the name of the algorithm?
Right now we're using Levenberg-Marquardt, but we actually, you can switch that up very easily. It's not dependent on what you choose. We found that some algorithms, so Levenberg-Marquardt is the best, except that there's occasionally a disk it just doesn't like, and it can't find a minimum, and then we can tell it to go use a different optimizer and try again. So different optimization procedures will give roughly consistent results. Yeah. Do I use what? Yeah. So and the penalty function is that it needs to try to satisfy force and torque balance. So it tries to simultaneously get those two to match while making the sum of the forces and torques be as close to 0 as possible, right? Because this operates on single disks, it's easily parallelizable, right? So it's a parallel, and our code is written in MATLAB, so this works out well.
Do you enforce the force from A to B?
We'll come to that in a second. Okay. So the algorithm does this, okay? One disk at a time going through. And they do borrow information, and you have the options like you could pass guesses from one can inform the other, and so forth. Okay. Now you have this problem of you actually do know more, as Eric pointed out, that at any particular contact, okay, like this one, it better be true from Newton's second law that the force on A matches the force on B. Okay. So if you try to enforce that, you'll get a different answer, right? These aren't. And we don't know which one is right or wrong or more right or more wrong. Okay, you decide what to optimize. So we have chosen to optimize force and torque balance on a disk. At Patrick's request, we've written a little code that goes through each contact and says, okay, the left A on B and B on A don't quite match. Would I do better if I substituted B for A, or if I substituted A for B? Do those beat the original guesses? And if they do, you can replace them. Okay? It turns out taking the mean is never better. We don't know why. Okay. So usually one of them is just slightly off. It just was a bad optimization, so replacing it with its neighbor does better. You've now destroyed the torque and force balance on the original particle at the cost of getting torque and force balance on the contact. Right? Those of you who are interested in optimization, it's an open challenge to how to optimize those all at once, which we don't currently do. Okay, so that's, this is what we do right now, sort of an annealing process after the fact to try to get closer to that. But the number of constraints grows with the size of the system, right? And an optimization process running all of those constraints simultaneously, I don't know how to do. So there you go. All right. Okay, so what do we do if we have forces? Yeah?
What is your force sensitivity curve?
I don't have a plot of that up here, but so in what units? In Newton? So in terms of Newton, so we can get. Oh, so the error is actually, interestingly, a percentage error, not an absolute error. So when we do a scatter, so actually but from the unbalanced forces, if we do a scatter plot of the left contact, the right, the left side and the right side, that gives us an estimate of our error, right? And those are 10%. They disagree to 10%. And it doesn't matter if it's a small force or a large force. I don't know why that's the case, that it's a percentage error. But it seems to be true. And we have trouble beating it. We haven't been able to beat that. Yeah. All right. All right, so this is a little bit of foreshadowing here. So one of the things you can get once you have all the forces is you can actually calculate force tensors. Okay. So we know the particle positions and we know all the contact forces, so we can actually generate the whole local stress in the entire system from this data. Right. And so we'll come to that down the road. All right. So do forces matter? So this is just a little thing. These are just sort of highlights of some experiments that indicate why we should go through all this trouble to find the forces, because it is actually a pain in the butt. Okay. So do the forces matter? So I'll cede to authority. Isaac Newton said they mattered, right? So I don't know if you've ever seen this, but in the Principia, he was trying to understand why liquids have viscosity. And this was a case that he made, mind you, without any benefit of an atomic theory of matter. That little bit of matter A pushes on B, which pushes on C, pushes on D, pushes on E. Newton's second law, E has nobody to push on. Right? So he has to split his force, and then you get force chains. Right? So he was trying to use this to understand where viscosity came from. It's not a great model of viscosity. But it's interesting that this idea that the propagation of forces through a material is fundamental to understanding it is extremely old. I'm talking mostly about granular experiments with friction. None of this is unique to that. There are scads of experiments on frictionless particles as well. The upper left are emulsions in 2D, emulsions in 3D, gel beads in 3D that are swelled with water, so they're essentially frictionless. The upper one is colloids. And all of these show images of these correlations. Okay. And so they seem to be a persistent thing that we want to try to understand. All right, so we can do things like, we listed that vibrational properties are hard. I'm going to tell you guys a way you can do it if you're willing to hack your particles. So we took our particles, drilled out the center of them, stuck a piezo inside it, glued it back together, and because it's a 2D system, we can run the wires out the side. You can't do this in 3D so easily. So advantage of the 2D system. Okay? And so we can take movies of how, in this case it's sound, but we've also done vibrational modes using the same system, how the sound propagates through the system. Okay? And while the images are quite slow, the piezoelectrics are nice and fast. Right? And so, and because the particles are real, you can build things into them. You can build stuff into your particles. And this, as people can do MEMS and all sorts of stuff, I think the days of smart particles are going to become more and more. Okay. So one of the things that we saw, for instance, is that if you send a pulse, a sound wave through this, so the blue is the original force chains, the green is the changes in them. Okay. And I'll have to play this several times. I hope it repeats automatically. Does it? It doesn't. I have to do it by hand. All right. So when you watch the next time, keep your eye on the purple dot. And when the green sound wave hits it, you'll see the piezo pick it up. Okay. The second time you run it, okay, I want you to watch where the green goes. Okay, so this one, watch that the sound wave travels to the purple dot and the piezo picks it up. There you go. Right. So what we're seeing and what we're hearing are the same thing. Okay. And this time I want to have you guys watch what the green pattern of propagation of the sound. So what do you see? Where's the green? It's on the force chains, right? So the force chains are themselves acting to some extent, I don't want to say the correlation's 100%, as conduits for the propagation of sound. Okay, so why would this be? So here's a graph of that, if you didn't see it. So the red dot, the gray dots are every place you draw a gray dot, it was one particle, where from a high-resolution images, we calculated the pressure on that particle. And from the high-speed movies, we calculated how much it went, the amplitude of the sound wave was going through it, just from going bright to dark. Okay? And we binned that data. Those are the thick black dots. And what you see is that the more pressure on the particle, the more sound traveled through it. Okay, so there's a correlation there. It's not perfect. Okay? There's a lot of scatter, but it's definitely true. So why would this be true? Well, we have the answer sitting right over there. Okay? That if you push two particles together, you increase the contact area between them, right? Okay? So if you push two particles together, you increase the contact area. Okay? So for the force law that we measured for these particles, which I showed you earlier, which was to the 5/4, they're not perfect Hertzian, the area goes as F to the 2/5. Okay? And 2/5 and 0.35 are approximately the same number. Yeah.
Do you know where all that scatter comes from?
Yes. So there, the number of different ways that sound can propagate in a granular material, there's surface modes, there's reflections, there's a whole host of other stuff going on. And so people who will often look at the coda, so the tail end of the signal, the multiply scattered events, as a way of extracting information about small changes to the pile. So the details of that sound propagation sort of encode almost everything that's going on. Okay, but then how to back that information out is not as obvious. Yeah. Okay. So what we've, yeah, go ahead.
I just wanted to ask, when the piezo is active, that effectively changes the radius?
So piezos can work in two modes. So you've probably mostly heard about piezos being used as actuators. You apply a voltage to them and they expand, right? But they also work the other way, that if you put stress on them, they give off a current, right? So that's what we're measuring. So when the sound wave goes through, it compresses the piezo, and we measure the very small current that results. Yeah, and it's proportional to the stress, so it's sort of nicely, they're very, very linear. Yeah. So we're not sending a voltage through them, and therefore, I have contemplated, and we didn't get it to work, trying to drive particles this way, but the piezos can't generate enough force to deform the particles. Yeah. All right, so another poll for you guys. So we've discussed simulations, that they actually have a spring between two centers, right, that models this delta overlap, right? So what happens if you run one of these models like I've described with a sound wave going through it? Would it know about this effect? So the model of the particle is that they overlap, right? That there's a spring between them, but in the simulations they don't actually deform, right? They stay spheres. They're just allowed to overlap. Okay? So in fact, when you do computer simulations of this using one of these discrete element models, okay, and ask if you see the same effect, and this work precedes ours. So we were expecting it to not depend on the pressure on the particle. But in simulations, so the size of the error here represents the size, the amplitude of the sound wave going through. And you don't see that bigger arrows are on bigger force chains. Okay? So these are discrete element simulations that have been incredibly successful at describing oodles of phenomena. Oodles of phenomena. And yet, this is a spot where they don't capture it, because the model didn't have any way to encode this increase of contact area, right? So being alert to differences, okay, says that you don't want to use these sorts of models for studying sound propagation, okay? That they aren't the right model for that. Okay, another place that force chains matter. They encode a lot of information about the system. Okay, so this is a well-known experiment from Bob Behringer's group. If you take a bunch of these particles and you either expose them to biaxial compression or simple shear, I think you'll agree those two pictures do not look alike, right? Okay, so by looking at the force chains, you can tell what the history of the material is. And that's because the tangential forces, right, and the rolling of grains and so forth are happening in response to the boundary forces. Okay? And so if you were to transmit sound through these, you could make a prediction, right? That sound would be transmitted differently through these, and so forth. That thermal conductivity might be anisotropic, right? That vibrational modes might have issues, and so on and so on and so on. Okay? And that's very, very easily seen in this network of forces. Okay, so I'm going to jump. I decided to include this because there was a poster on rheology last night, and we've talked. But this, I think the force chains have an influence on the rheology. So these are experiments that my grad student Jutong is doing, and these are 8,000. These are literally the same particles I've been passing around. These are a sample of the same one. This is a meter across, basically. It's like a rheometer. You spin the inner wall, you measure the force on it, and you follow what's going on. And we have built a set of leaf springs into the edge. Okay? These leaf springs can dilate and can twist in response to boundary forces. You can calibrate that. Okay? And you actually can measure, at each of these tips, you can measure both what the normal and the tangential stress is at each of those tips. Okay? So we have a system where we know the boundary stresses and we know what's going on in the material. And there have been various theories, non-local rheologies, that try to understand what the slow flow of granular materials are. Okay, so places where you're below the yield criterion, where you don't expect the forces to be able to slip, the contacts to be able to slip, nonetheless do slip. There's creep. Okay, so if you have small vibrations in one part of the flow, they can influence things and cause areas of the flow that are below the yield criteria. So the tangential force is less than mu times the normal force. They can still be mobilized. Okay? So these rheologies are based on trying to understand that. I'm not going to go into the details of it. I'm just going to point out that they exist. And that, in fact, they can fit the stress, the ratio. We want to study rheology. You often look at, this is like stress versus strain rate. Okay? These are non-dimensionalized, and these theories can fit the data very, very well. Okay. One of the things that they depend on, okay, is a divergence in a correlation length near this failure criteria. Okay, so the theories say that if you're close to this failure criteria, the system is cooperative. It knows about what's going on elsewhere in the system when you're very close to that. And this sounds a lot to me like a susceptibility. Right. Okay, so we took the data and took movies where we measured the force chains. We took pictures of the force chains. Okay, and in each ring, we measure how much the force chains fluctuate. Right. So during the course of the movie, just bright and dark. Not even the fancy stuff I just told you about. Just bright and dark. Okay. And we measure those fluctuations at a bunch of rings stepping out. Okay. And we also know, because we've calibrated the boundaries, what the ratio of tangential to normal stress is, and we know the velocity profile. And wouldn't you know, okay, that at the point where we believe the yield criteria to be, that's precisely where the fluctuations stop. Okay? So the force chains can't fluctuate, okay, when they are below the yield criteria, and they can above it, which looks a lot like susceptibility. So the force chains are encoding information about how the rheology of the system will behave. So this is something that's not so related to this group of you here, but I wanted to point out these force chains have implications more and more. All right, a few things. All right, you guys, a lot of you guys have models. So you want to find data to test your model, okay? And now you're warned about all the problems, but you still think it's worthwhile, right? So how do you go finding someone who has the kind of data you want? And you know not to ask about contacts, right? Okay. So one option is there was actually just published a RSI put out a special issue on imaging techniques in granular physics. So there's 10 articles describing 10 different techniques. It was part of a summer school last year, and basically, if you care about velocities, or you care about vibrations, or you care about anything, these articles will tell you who the groups are who are taking that kind of data. Okay, and then you can call them. Okay, find out, look for them at their next conference and start talking to them. Okay, and you are now empowered to not make a fool of yourself asking for things that are difficult, because you know what's hard and what's easy, right? Because you can be brave and go do this. Let's say you're shyer, okay, and you don't want to go, hitting up strangers for data. Okay, there are people who publish their data. Okay, so this is just one example. So let's say you saw Matthias Schroeder's paper on the disordered packings of tetrahedra, and you have an idea that you think you know why it behaved as it did. Well, he published his data. You can just go download it. And the cool thing is the data has its own DOI, which means you can just cite the data specifically, right? So this is a brilliant plan. And I say brilliant only because I know the people he's making fun of me. He knows why I think the people involved are brilliant. And so here's the deal. Those of you who are experimentalists, what do you gain if you put your data up there? Well, one, do you honestly think you're going to analyze every last aspect of your data before you graduate? Right? No, you don't. You probably won't, right? Okay. So by publishing your data, okay, while you're still analyzing it, not waiting until you've forgotten which disk it's on and whether it was in newtons or in volts, okay, you publish it, okay, you're freeing up the other 2/3 of people in this room to do other cool things with it that you never even thought of, okay? You have just increased the impact of your work merely by publishing it, the data itself. Okay, so do I put my money where my mouth is? I'm starting to. Okay, there's a reason that I do have stuff up there. It's not stuff that'd be of interest to you, but my goal is to have the data that my lab publishes from now on be up there, and I would encourage those of you who are willing to be brave enough to do it to do it. Okay, and it does mean exposing yourself to the flaws in your data. Okay, so it's a little embarrassing. There's a risk that your underwear will be showing. But those problems were there anyway. So I'd encourage you guys to check it out.
Do they have limits on the size?
There are some limits, and you actually pay a small fee. But there are some journals that will pay those costs, some won't. There's all sorts of different negotiated agreements. Yeah. There are also other services. People use Figshare. Some universities have their own repositories that have good archiving processes, in which case you can just do it at your own university. I would encourage you guys to look for some place that has a data. They actually post on their site like what their long-term archival strategy is, right? Because remember, this isn't stuff like a journal where the printed copy is still in some library, right? I mean, this is stuff that you're sending them data, and it could decay for all the reasons that data decays, right? So it's definitely worth checking out that they have a good system. They give you a DOI. That makes it easy for people to cite it and to find it. You get to publish the data DOI in the paper, so people are reading the paper say, I love this data. I wish the authors had done this. They'll just go do it, right? And often they'll contact you and maybe want to collaborate. Sometimes they will, sometimes they won't. Okay. But it reduces you having to talk to people, right? Once you've published the data, it's out there. You don't have to go scrounging to see which disk it was on 7 years later. Okay. All right, the last thing I want to do before my time runs out is you've seen on the schedule that there's a Monday workshop. I want to say a little bit about that, what that is. So it says it's a workshop on negotiation skills for women in physics. And that's because the APS, American Physical Society, has funded a bunch of us, that's this link here, to go forth and teach people to negotiate. And why women? And since I know my internet's not on, this is not going to work. When you, the data for salary gaps in academia between women and men has been growing over the last 20 years, not shrinking. And this is disturbing. Okay. Now, why? So that's a reason for women to learn how to negotiate. Why? So one of the reasons why this happens is this little graph right here. So this is a famous social science experiment in which they asked, who's done these psychology experiments for credit as an undergrad? For pay, for whatever, right? Okay, so I think it's a common American thing. You sign up to be part of someone's thesis. They come in, they give you hearing buds, you raise your hand if you can hear the sound or if you can't, right? They never really tell you what they're studying. So this is a psychology experiment where they told them they were studying something. And they said, you'll be paid between $5 and $10 for participating in this study. And at the end of the study, they gave everyone $5. And the first column is who asked, could I have 10? You told me it would be between 5 and 10. You only gave me 5. This is the percentage of women who asked for $10. This is the percentage of men who asked for the $10. Okay? This can lead to salary gaps, right? Okay, now, it's also true that 75% of the men did not ask, right? So let's be clear. So this has become known as the Women Don't Ask study. Okay, they redid the study where they asked people, like, is that okay? They gave them like a hint, like that, like it's negotiable, right? And that definitely improved things. Okay, so the goal of this workshop, and if any of the men want to come, they are welcome to come as well. Okay, is to talk about some of the strategies that people who are in this 97% are willing to use to not do to get over this. And in fact, some of these strategies are different for men and for women. There's things that if men did them would seem weird. There's things if women did them, they were seen weird because we're socialized to behave differently in society. So this is definitely a gendered workshop. I'm a woman. I negotiate as a woman. I can't help not doing that. But it doesn't matter if you know what you identify as. You are welcome to join us on Monday night. And it'll be a hands-on. It'll be practice. We'll actually practice negotiating and stuff like that. All right. And now for the part you've been waiting for, your homework. Yeah. So if you come to the workshop, you'll also hear about things I have not negotiated for and am mortified about. And that's the reason I run the workshop, because I'm in that 97% in my history. All right, your homework, should you choose to accept it. I hear tell is a sand court near Smith Hall. I have seen the volleyball at the Buckingham front desk. So your homework. So check out the volleyball, bring it to the volleyball court, and perform some sort of experiment on the sand in that sand volleyball court, which is real sand, not made of spheres, and either take a photo of your experiment or make a movie and send it to me, illustrating something that you've learned in the past 2.5 weeks. Okay, so that's your homework, and then you pick up the volleyball, and even though it's a single particle system, go ahead and play that. Right. So we will continue with the theoretical frameworks, putting all this together on Monday. Thanks.